space is just a differential equation, but we write it in a special way. X dot equals ax plus bu, and y is my output, cx plus du. Okay? U is the input, and y is the output. Okay? So maybe a model will be something like x1 dot x2 dot equals 0, 1, negative 1, negative 2, x1, x2 plus 0, 2 pi times your input, which is u, and the output, which is left, is 1, 1 times the x's. So again, this is very legitimate unsteady model, right? Give me the input alpha, this is alpha, which is the u, and this is output, the left. This is a very legitimate way of describing unsteady aerodynamics, and this is a very legitimate way of describing unsteady aerodynamics. And remember, from 170 concepts, if you have the transfer function, you can easily get the state space model. If you have the state space model, you can easily get the transfer function. Here I'm just giving examples. This guy is not the state space model corresponding to this transfer function, right? This is just the first order ODE, whereas this is second order. I'm just giving examples, okay? At MATLAB, you know, there is the SS to TF command and TF to SS, from transfer function to state space and from state space to transfer function in MATLAB. This is for linear dynamical systems. Actually, we cannot write a transfer function for a nonlinear system. There is nothing called, you know. All these are for linear because during this entire course we will be also confined to potential flow, two-dimensional, linear, small angle of attack, this all naive things that we used to. We will have some, you know, some touch upon some viscous effects towards the end, some effects of nonlinearity and high angles of attack towards the end. But the main focus will be to develop a model, even in the small alpha regime, even if you're oscillating between 5 and negative 5 degrees angle of attack, it's not very obvious how to determine the corresponding lift from the alpha oscillation. It's not 2 pi times alpha. And you will see that there is a whole theory behind it. What else? How can I represent, if it's a linear system, how can I represent the dynamics? Any idea? If you are in the lab, so if I'm knowledgeable enough and I'm clever enough in mathematics, I can derive a transfer function or I can derive a state space model. You can derive these from first principles. You write down your electrical, the equations governing your electrical part, governing your mechanical part, your thermal part, combine them together, and develop your transfer function like you used to do in 170. But if you are in the lab and your system is kind of a black box, can you tell me how to get your dynamical system representation? There are several ways, but there are two very famous ways. Let's get one of them. The what?
Will it be a block diagram?
The block diagram needs, yeah, the block diagram is just description, but it's not quantitative, right? I need something quantitative like here. Boolean plot, this is very good, yes. Boolean plot, I'm going to talk about. So this is one of the two ways. What's the other way? This is very easy, step response. If your system is rich enough, go and give it a step. So by the step response we mean the transient. Okay, so this is the definition of the step response. Let's see here, what's the step response? So you have your input as a function of time, u, which is here it's alpha as a function of time. You give it just a step change from 0 to whatever, maybe 1 degree, okay? Constant. And you go and get the corresponding output as a function of time. If the system is stable, it will just go something like this, or like that, right? And it turns out that over this time, so in this curve now, this is the output, which to us in aerodynamics, it's the lift, for example. I mean, you may be interested in several things like drag as well, separation point, circulation, whatever, but let's say the lift for the moment. We will spend quite time with the lift as our output. So over this time, this is, if you recall, this is the settling time. During this period, this is what we call the transient response, right? The transient. After the transient response, you have the steady response. So this value doesn't indicate anything about the dynamics of the system. This value is simply the 2 pi times this guy, 2 pi alpha. In controls, we call it the DC gain. So the DC gain for our transfer function is just 2 pi. But turns out that this period only bears all the dynamics of the system. If you give me just this shape, I completely know anything about the system. It's exactly as if I have the transfer function. It's exactly as if I have this moment. Can you tell me a very quick approach to get the transfer function? What's the transfer function? By definition, brute force definition, Laplace output divided by Laplace input, right? You have this guy in the time domain, try to match it some time equation, get the Laplace, you have the Laplace of the output, and divided by what? Which is 1 over s, right? Is the Laplace of the input, it's the step. So if you have this guy, I can get the transfer function. If you have the transfer function, you get the Sitz model, whatever. So if your system is simple enough, by a single experiment you can identify your dynamics, or a good representative model of your dynamics. So again, this is the transient, okay? Just keep in mind, the transient response. What really matters is the very first 2-3 seconds. After that, you will have the steady response, which I don't care about from a dynamical perspective. The transient response due to a step input. Okay. And I will introduce the fourth method, which we will deal with in this class. Which you told about, what's your name? I'm sorry?
Me? Zahal.
Zahal?
Yeah.
So Zahal said about, so reminded us about the, so this is the fourth thing, the frequency response, which sometimes we call the Moody plot. So the step response, and this is the frequency response, sometimes they call the Moody. This is a little bit more involved. It's not as simple as the step response. But it's easy to execute if your transient dies quickly. If your transient dies quickly, and remember here we need to measure the response in the very first couple of moments, okay? The very first few seconds. So if your instrumentation is not accurate enough during this period, you will not be able to use this method to identify your system. This is another completely different way of doing it. I'm just reminding you, so when you have a linear dynamical system, and you give it an input that is oscillatory in nature, A cosine omega t. Okay? So if it's an airplane, you're playing with the elevator with some amplitude and frequency. If it's your car, you're playing with your gas pedal with some amplitude and frequency. Okay? You're giving your input as an oscillatory input, it's not just a constant input. And this is for obvious reasons. You're trying to excite the dynamics of the system. It's not just giving a constant input, fixed input. No, I'm exciting the dynamics of the system. Okay, so what will I get if I have a linear system? What will I get? Well, I'll get an output that is also oscillatory, cosine, the same omega, the same frequency. So if my input is slow, the output will be slow. If it's fast, my output will be fast. But with two different things. I'll have a different amplitude, and I'll have a phase shift. Okay? Just to give you an idea about that, so this is your input, u as a function of time, which is alpha to us, and this is your output, y, which is CL. In the frequency response, in contrast to the step response, we are interested in the steady state. So the frequency response is the steady state response due to a harmonic input. Okay? So you give an oscillatory input. So at the beginning there will be some transient, right? I don't care about, ignore it. Ignore the transient, I don't want to see it. I will identify the dynamics from the steady state response, but the steady state response is not now a constant. Why? Because you're not giving a constant input, you're giving a time varying input, so your output will follow your input. So I will have a cosine waveform with a different amplitude. This is B, whereas this was A, and I will have a phase shift. So maybe this is peak and this is peak. This gives you the lag of your system, which is related to the phase shift. Okay? Okay, so that's okay. I get my output to follow my input, but it's not exactly the same amplitude. So maybe larger, maybe smaller, and your frequency response shows that. So your output amplitude is your input amplitude times the magnitude of your transfer function, and this phase shift phi is the angle of your transfer function, and the frequency response, if you remember, the Booty plot is just exactly these two figures. It turns out that this magnitude depends on the frequency, and the phase also depends on the frequency. And this is very important to realize. So what do you mean here? What do you mean when you have this figure? If someone magically gave you this figure, how to interpret? So at this frequency, you go here, you get maybe half. Okay? And at this frequency, you go here and get maybe negative 45 degrees. What do you mean by that? Okay, so it means that if you give an oscillatory input, a cosine wave or sine wave, you will get an oscillatory input the same speed, but with half the amplitude. Okay? With half the amplitude. So you're losing some of your, if the output is my left, I'm losing some left, right? I'm losing half of my expectation. And I'll get it later on in time. There is some phase lag, which is expected. Okay? So, for any typical mechanical system, it looks like this, which we call low-pass filter. So the higher the frequency, the lower the magnitude that you will get. Okay? And this invokes the definition of the bandwidth. What's the bandwidth? Is the range of frequencies over which you consider your system satisfactory, beyond which it almost gives you zero. Okay? Any question about that? If you have any question, please stop me. So you can construct this in the lab. This is actually what Joseph is doing in his experiment. And like I said, from the frequency, remember, all these representations, we have seen 4 representations now. Transfer function, state space model, step response, frequency response, they are all equivalent for a linear dynamical system. If you have one, you can get the three of them. Okay? Any question about that? So you can see that all the stress here, so this is why it's called, the course is about unsteady aerodynamics indeed, but the name says dynamics of unsteady flow or unsteady flow dynamics. Why? It's just to stress this dynamical perspective. We're treating our flow field as a dynamical system. It's no longer an algebraic relation anymore. It's a dynamical system. You represent it by a transfer function, by a state space model, by a step response, by a frequency response. And please go and review these 4 things from your 170 course. Okay? We'll not have time to review them here. We'll go ahead as if you know them completely. If you have any questions, just stop me. Okay. So actually, in 1925, this is one of the earliest papers on unsteady aerodynamics. Wagner, he determined the step response of the lift due to step change in the angle of attack. So he said the lift as a function of time, maybe CL, is the CL steady as a function of time. There's a number. What's this number? Can you give me a relation of this number? How can I get this number? How can I get the steady lift coefficient? It's just 2 pi alpha, right? Time is a function of time. This is called the Wagner function. And this is the Wagner function. This paper is written in German and has never been translated up to my knowledge. It would be great if some of you knows German and translate it. You can get some credit in this course. But I mean, you can follow after you know, I mean, the tools that we're going to learn in this course, you can follow the paper, that's fine, but we don't know exactly what he writes, or at least I don't know. So this is CL, this is time, this is the steady state value, which is 2 pi alpha. There is a function that gets you from here to there. This is the unsteady response. This is, which is 5t. So you can see that 5t goes to 1 and t goes to infinity, right? So 1 multiplies this steady value so that the unsteady lift recovers the steady value after some time. Any question about that? So one of our objectives in this course is to study how Wagner did it. Okay? How to derive Wagner's function in detail. And he did it for small change in the angle of attack, 5 degrees. If you want to do it for larger angle of attack,